So let's make things a little bit more interesting, which is the same setup, same magnetic field, same bar, but now the bar is going to move on a rail. So let's do a setup like this, a cable, you bend it this way, you bend it this way. Okay, and now your bar is going to be sitting on top of that. And again, your magnetic field is still everywhere in space pointing into the page. And the bar is moving that way, velocity v. Something is making the bar move that way. So now what happens? The red line that you see there is a cable, it's a conductor, and the bar is sitting on it, in direct contact with it. So because the bar, the top of the bar acquires a positive charge, and the bottom of it acquires a negative charge, and those two sides of the bar are now connected by a cable, right? You would expect that there will be a current out of the bar going this way, down on this cable, back to the bar. That positive charge that moved down the red wire, when it arrives here, right? Now that that positive charge has canceled some of the negative charge, the electric field inside goes down. So what is the result of that? The magnetic force now wins and pushes the positive charge towards the top. So the positive charge actually continues to flow inside the bar. When it gets to the top, it has a path to go and join its brothers, the negative charges on the other side, and it will go do that. But once it gets there, the magnetic force pushes it through the bar again. So this charge continues to flow. So you have set up a current here in this circuit, just by moving the bar with a velocity v. The charges, because they have the same velocity as the bar in the x direction, those charges experience a magnetic force, right? That's what we just said, and that's the magnetic force that pushes the charges up that bar. This was the magnetic force, right? But once the charges are moving in that direction, there is an additional force that will act on those charges. Because now you have a velocity vector pointing this way, and you have a magnetic field pointing that way, right? So when you put your right hand, the thumb pointing in the direction of v, the fingers pointing into the page, you see that the force now, there is an additional component to the magnetic force, which is now pointing to the left. So those positive charges now have, once they're moving and circulating in this circuit, those positive charges inside the bar, the magnetic force on them has two components. One component is along the bar, that would be this one, because those charges have a velocity in the x direction, the same as the velocity of the bar. But because the charges are flowing up, there is a new component that develops, which is this one, that is actually putting a force on the bar. That force, when you add it over all of the positive charges inside the bar, will be something significant. That will be a force that you would feel if it is you holding on to this bar and trying to make the bar move with constant velocity. You would experience an opposite force, a resistive force, coming from magnetic force acting on the current that is flowing in the bar. Okay? How much is that force? Well, if I know, if I have a wire with a current I, the wire has a length L, and it is in a magnetic field, that is the force on that wire, right? That one is given by this, and now you can say, well, how much is the current that is flowing in this circuit? If the difference in potential between the top and the bottom, we just calculated in the previous equation, right? That difference in potential was LVB. Remember, this was the electric field inside the bar. This was the distance, the distance between the 2 points, the top and the bottom. So that is the delta V, right? We call it delta V. So I replace that, LVB for the electromotive force divided by R is my current. So the magnetic force that is pointing this way, right? on that bar, that magnetic force is going to have the following magnitude. The current, which is LVB divided by R, multiplied by LB. So I can write this as V L square B square over R. So this is the force that is going to oppose your hand trying to keep this bar going with constant velocity. You will feel that force. And notice that is proportional to the velocity, so it's sort of like a frictional force, like air drag, for example, or the force that when something is falling in a liquid, the viscosity force also depends on, is proportional to the velocity. So the faster you're trying to make this bar move, the stronger you're going to have to pull on it. Because the reaction force, this Fm, is going to be proportional to the velocity. Now you might wonder, well, if you have to apply a force to this bar, that means that you're going to have to do some work. To keep this bar moving, you're going to have to do some work. You're going to have to apply a force, an external force, to compensate for the fact that there will be a magnetic force trying to slow down the bar. And to keep this thing moving with constant velocity, those two forces need to be equal, right? Now, if you have to apply a force to this bar, that means you have to do work on that bar, right? And if you're doing work, you're also producing some power, work per unit time. So if you remember, the power of a force, in this case the external force, is going to be equal to the magnitude of the force multiplied by the velocity of the object on which this force is acting. So that external force is going to have to be equal to the magnetic force to keep this moving with constant velocity. So you're going to have VL square B square over R multiplied by V. That will be the power that you have to put in this system to keep it moving with constant velocity. Now, where is that energy going? I'm putting energy into the system by applying a force over a distance. I put in energy into this system. Where did that energy go? It should be thermal energy, because when you do that, you get a current flowing. Remember, this bar is part of a circuit, and we figured that there will be a current flowing in that circuit. And because there is a resistance in the circuit, whether it's on the bar or on the cable, wherever it is, there is a resistance, then there will be dissipation of power. And the amount of power dissipated will be equal to the current square multiplied by R. If energy is conserved, what can I say about the power of the hand pulling on the bar and the power being dissipated by the resistor, by the resistance in the circuit? If to keep this bar moving with constant velocity, I have to put in 10 joules of energy per second, those same 10 joules of energy per second should be dissipated by the current, right? So what I can say is that the power of the external force, which I just calculated here, this is going to have to be equal to the power dissipated by the resistor in the circuit, right? They should be the same, or energy would not be conserved. Are those equal? Can we tell easily that whether they're equal or not? Well, let's write the current. The current is right here. Power is I squared times R. Right? So if I square that current, what do I get? The current square, according to this, is going to be equal to L squared V squared B squared over R squared. If I multiply by R, which is what I need to get power, right? And you get exactly the power put in by the hand pulling on the bar, is L squared V squared B squared divided by R. You have it here. Okay? So just another way to check that energy is conserved, of course, as you would expect.